Well, friends, students, friends, we have one more simple derivation of coefficient of self-diffusion on the basis of transport phenomena. This is transport phenomena known as transport of mass. I have drawn here the figure, same figure I have modified. So we have layer AB, and this layer AB is having concentration of the gas molecule N. Above this layer AB, we have considered one more layer, that is EF, and the concentration of this, that is N plus lambda dN by dz. So along OZ we have the distribution of molecules, that is concentration of the molecules OZ, and at equilibrium condition the concentration parallel to OX for all the layers it is constant. That is at equilibrium condition, that is a final stage, but we don't want that. We want how it reaches to the final. What happens when a steady state means unsteady state begins, and we have started with unsteady state and we are going for a steady state in a transport phenomena. AB is the layer, it is away from EF by distance lambda, or EF is at a distance lambda above the layer AB, and here the concentration is N plus lambda dN by dz. dN by dz is dN by dz, here concentration gradient of the molecules, gas molecules, and this gradient, concentration gradient, increases uniformly or gradually with a distance. The concentration of the molecules in the layer CD, which is just below the layer AB at a distance lambda, is given by N minus lambda dN by dz. To start with what is called as self-diffusion, and the self-diffusion is due to the transport of mass from region of higher concentration to the region of lower concentration, and it brings about an equilibrium state or condition. So consider a gas having concentration gradient dN by dz along this OZ. Let N be the number of molecules per, that is, of course, N be the number of molecules per unit volume, and here N is the concentration of layer AB. Consider two more layers, that is EF, a layer above the layer AB at a distance lambda, and one more layer CD which is below the layer AB at a distance lambda, the mean free path. 2. Concentration of the molecules at the layer AB is given by this N plus lambda dN by dz, and concentration of the layer CD is given by N minus lambda dN by dz. Now the number of molecules here coming from the layer EF crossing the layer AB in downward direction per unit area per second are equal to, that is, I will repeat, the number of molecules coming from the layer EF and crossing the layer AB per unit area per second are equal to 1/6. Here it is number, it is a concentration, only the molecules, C, no mass, okay, into n plus lambda dn by dz. This is, and the molecules going up, coming from the layer CD, crossing this layer AB per unit area per second in upward directions are equal to 1/6 C, the average velocity, into n minus lambda dn by dz. This third derivation is very simple compared to other two. Now, therefore, the net number of molecules crossing per unit area of layer AB in downward direction is equal to net number of molecules crossing per unit area of layer AB per second in a downward direction is equal to 1/6 C n plus lambda dn by dz minus 1/6 C n minus lambda dn by dz. And if you simplify this will be equal to 1/3, same as earlier, C lambda, say dn by dz. Now, what is called as self-diffusion? See, it is a self-diffusion is defined as a ratio of number of molecules crossing per unit area in 1 second to the rate of change of concentration with a distance. So here the number of molecules crossing, what is called as self-diffusion, is defined as the ratio of the number of molecules crossing per unit area per second of the layer AB to the, say, concentration gradient, that is D. Coefficient of diffusion, I will write here, coefficient of diffusion is defined, coefficient of diffusion, coefficient of self-diffusion, this is D is equal to this 1/3 the net amount of or net number of molecules crossing per unit area of layer AB in 1 second. The 1/3, say C, the average velocity lambda dn by dz divided by this, that is by definition dn by dz. So the coefficient of diffusion is given as 1/3 C lambda simply. The coefficient of diffusion is given by this relation, a simple derivation. Well, the effect of temperature and pressure on diffusion, let us say effect of temperature and pressure on diffusion coefficient, say D, it is denoted here D. Let us write, we know this lambda the mean free path, it is given in terms of pressure kT root 2 pi sigma square into P. We have derived this, and average velocity C average, let me write here, average velocity is given by under square 8 kT. It is the absolute temperature per m. This is average velocity. Let us substitute this lambda and c, average or c, in this relation. That is 1/3 c is, say lambda first, say kT upon root 2 pi sigma square P pressure into this, that is under square root, it should be, let me, under square root 8 kT upon per m. Now if you simplify this, this will be equal to, say 2/3, that is thus 2/3, say 1 divided by sigma square P root m, that is here, per, it comes out. So this is into kT upon pi raised to 3/2. Now this is coefficient of diffusion. From this we can show that, this shows that the coefficient of diffusion D is directly proportional to absolute temperature to the power 3/2. And here look at this coefficient of diffusion is inversely proportional to pressure. Inversely proportional to pressure. Look at the relation between pressure of the gas and, say, viscosity and thermal conductivity and pressure. See, viscosity is independent of pressure. Thermal conductivity is independent of pressure. Whereas diffusion is, D is inversely proportional to pressure. Inversely proportional to pressure. Look at this. It is simple thing. Now, let me write the relation between what is called as eta, the coefficient of viscosity, and, say, diffusion. Coefficient of diffusion. So, relation between say eta, the coefficient of viscosity, and the coefficient of self-diffusion D. Let me write this eta, the coefficient of viscosity, that is 1/3 rho, the density of the gas, c, the average velocity into lambda, and D, the coefficient of diffusion. Coefficient of diffusion is given as 1/3, say c into lambda, which we have written here in this expression. So D is equal to 1/3 c lambda. We have, say, eta upon rho. Now D is equal to eta upon the coefficient of viscosity upon the density of the gas. But this relation, theoretical relation, doesn't hold good. So they have modified this. Therefore, the modified relation between, say, coefficient of viscosity and the coefficient of viscosity and the coefficient of self-diffusion is given by D is equal to, say, some f dash eta upon rho, the density. Here the factor eta means factor f is a numerical factor. F dash or f prime is numerical factor. Many times we come across such numerical factors in physics, and this numerical factor f dash is equal to 1.4. Is equal to 1.4. When they have included this factor, this relation seems to be hold good when they verify this concept or a transport phenomenon experimentally. Well, I appeal all the students of second sem who have obtained physics, please do not keep yourself ideal, means do not sit ideal. Say when you are free, you are staying with your parents, you are at your home, and we are sending the online video classes. Please go through those video classes and go through the notes and try to understand the subject here. There is a time with you. Don't sit ideally doing here and there unnecessary things. Do some, say, a good work that is going through your syllabus, going through each topic. Students, friends, I have completed here the second part of this kinetic theory of gases. No doubt we'll solve some numerical problems for 1 or 2 sessions, that is on the first part, that is on the second part, as well as on the third part. Let me start tomorrow what is called as Brownian motion. Brownian motion tomorrow or in a second, say, or next week. Let me see whether I can go for the other classes. I will stop here for temporarily and then I will continue. But today I have uploaded all the notes related to this. My request, humble request to you all is, you are at home, you are staying, you are enjoying your stay with your parents because of this pandemic situation, and we are busy. We have kept ourselves busy in taking the classes without students. We are speaking simply, or ideally speaking, we are speaking with this benches, tables, or we are speaking with ourselves. We are playing with these boards and books. Please make use of this. Please make use of this. And if you are making use of this, definitely you are not spending your time, or you are spending your valuable time on a constructive work instead of doing, say, unnecessary or a destructive work. Thank you.